This is lesson 27 in our Calculus 3 series, Cylindrical Coordinates. In the last lesson, we saw a couple of triple integrals where after we described the bounds on z, we realized that it would be best to describe the other two variables in terms of polar coordinates. So for example, we had find the volume of the solid between z equals 16 minus x squared minus y squared and z equals 3x squared plus 3y squared. We realized that after we described the bounds on z, we had 3x squared plus 3y squared down here and 16 minus x squared minus y squared here. We realized that the circular domain would be most easily described in polar coordinates. So instead of using x and y, we chose to use r and theta to describe that two-dimensional domain. So we had dz, and then instead of dx and dy, we had r dr d theta. So we bring that r in, and now we've got a triple integral in r, theta, and z. Now, more generally, we can describe points in three-dimensional space instead of in x, y, z coordinates, but in r, theta, and z coordinates, and that's called the cylindrical coordinate system. So using r, theta, and z to describe points in R3 is a cylindrical coordinate system. So r and theta are exactly the same thing that they are in polar coordinates for the two-dimensional plane, and then z is the same z that we've had, being the height from the xy plane. So we have the same relationships between x, y, r, and theta, and z is just equal to z. So any point in three-dimensional space can be described either by its x, y, and z coordinates, or by its r, theta, and z coordinates. This is one natural extension of polar coordinates into three-dimensional space. Here we're given r, theta, z to be 1, 5 pi over 4, 3, and we're looking for x, y, and z. So of course the z stays the same, and we want to find the x and y coordinates to go with these r and theta values. Well, we know that x is equal to r cosine theta, and y is equal to r sine theta. So 1 cosine 5 pi over 4 is equal to negative radical 2 over 2, and that's x. 1 sine of 5 pi over 4, also equal to negative radical 2 over 2, and that's y. And so now we have the corresponding rectangular coordinates for the same point. Taking a look at this example, we have r theta z to be 2 pi negative 1. Again, our z coordinate just carries, and we need to change the r theta to x and y using the same equations, x equals r cosine theta, y equals r sine theta. So in this case we get x equals negative 2 and y is equal to 0. And so our x, y, z coordinates are negative 2, 0, negative 1. Now we can also go in the other direction and convert to cylindrical coordinates. So that means we want to change our x and y to r and theta. But remember, just like with polar coordinates, there's not going to be just one way to express a point in polar coordinates. Same thing here, there's not just going to be one way to express a point in cylindrical coordinates. Remember that you could have positive r values and negative r values. You could also represent your angles by adding 2 pi. But here we're looking for at least one way, the simplest way we can think of. And we'll talk about the other options as we come across them. So let's find r here. We know that r squared is equal to x squared plus y squared. So here we have r squared is equal to 4. So we could choose r to be positive or negative 2, and we're going to choose the simpler version with r being positive. So let's choose r equals 2. We know that since x equals r cosine theta and y equals r sine theta, we have tan theta is equal to y over x. So in this case, tan theta is equal to 1 over radical 3. Now, we can't just simply say, okay, theta is equal to arctan of 1 over radical 3. It's not quite that simple. Remember that there are more solutions to this equation than there are to the one that says theta equals arctan of 1 over radical 3. Arctan is a function and gives only one angle result here, yet there are infinitely many angles theta such that tan theta is equal to 1 over radical 3. So if we want to solve this equation, tan theta is equal to 1 over radical 3, we're going to look at the arctan of 1 over radical 3 and then check to see which quadrant our point is in so that we can use that as a reference angle. Now we know that arctan of 1 over radical 3 is equal to pi over 6, but now let's take a look at the x and y coordinates we were given. X and y are both negative. That tells us we are in quadrant 3. We're in quadrant 3 with a reference angle of pi over 6. So our theta is equal to 7 pi over 6. And so we have r is equal to 2, theta is equal to 7 pi over 6, and the z is the same as it was in rectangular coordinates, and that's negative 2. Now notice, for this 7 pi over 6, we could have called this negative 5 pi over 6, and we could have a radius of positive 2 with an angle of negative 5 pi over 6. That's also a valid answer. We could have also taken r to be negative. If r was negative 2, we would need an angle of pi over 6, so that we're going backwards in the direction of pi over 6. So we could have negative 2 and pi over 6, but we never do that, so don't do that. We could also add and subtract multiples of 2 pi to this 7 pi over 6. But we want to keep things simple, so we want to either use 7 pi over 6 or negative 5 pi over 6. Now let's take a look at another example. Here we have x, y, z is equal to 0, negative 3, 1. So again, we'll start by finding r. We have r squared is equal to x squared plus y squared. In this case, that's 9. So r could be positive or negative 3, and again, we're going to choose a simpler version, choose r is equal to positive 3. Now, we can't use tan theta equals y over x in this case because x is equal to 0, and this does not exist. So let's take a closer look at our point and find our theta value. Here we have xy as 0, negative 3. 0, negative 3 is this point down here. So how can we represent theta for this point? Well, we could either represent it as 3 pi over 2 or negative pi over 2. So when x is equal to 0, one way you can find theta is by plotting the point and recognizing the angle from your plot. But you could also use formulas to get it. We could use, for example, the formula y equals r sine theta, plug in the y value, plug in the r value we just found, and we have here that sine theta is equal to negative 1. So again, either theta is 3 pi over 2 or negative pi over 2. Certainly we can add and subtract multiples of 2 pi to these solutions, but we don't want to do that. We want to just keep it simple. So our solutions would look like 3 pi over 2, 1, or 3 negative pi over 2, 1 for r theta z. Now let's take a look at surfaces in cylindrical coordinates. And let's write these equations in cylindrical coordinates. So here's a surface z equals x squared plus y squared minus 2xy. Well, we know that x squared plus y squared is equal to r squared. So that gives us the r squared here. And then x is equal to r cosine theta, y is equal to r sine theta. And then we would just simplify a little bit. And so we have r squared multiplied by 1 minus 2 cosine theta sine theta. And now we have our equation in r, theta, and z. Now let's take a look at x squared plus y squared plus z squared is equal to 16. Again, we have our x squared plus y squared here. We know that's equal to r squared. So we get r squared plus z squared is equal to 16. And that's our surface written in cylindrical coordinates. Now let's convert these equations to rectangular coordinates. Let's take a look at r is equal to 2. Well, the equations that we have that convert between polar and rectangular coordinates have x squared plus y squared equal to r squared. So let's square both sides here. R squared is equal to 4, and then x squared plus y squared is equal to 4. In two-dimensional space, that's a circle of radius 2 around the origin, but in three-dimensional space, in cylindrical coordinate space, that's the cylinder x squared plus y squared equals 4. Looking at the equation theta equals 3 pi over 4, let's think about that before we solve using equations. Theta equals 3 pi over 4. Here's our x-axis and our y-axis. Theta being 3 pi over 4 tells us we have an angle 3 pi over 4 from the positive x-axis, so that tells us in two-dimensional space we're talking about this line of points. it would be all the points in the two-dimensional plane. R could be anything, but theta is 3 pi over 4. But now in three-dimensional space, we have no restriction on z. So in three-dimensional space, we've got an entire plane of points. But now let's see how we can get the same idea using the formulas. Well, we know x is equal to r cosine theta, and y is equal to r sine theta. So let's plug in this theta and see what relationship we can find between x and y. If we plug in theta equals 3 pi over 4, we get x is equal to negative radical 2 over 2r, and y is equal to radical 2 over 2r. So this says x is equal to negative y, or y is equal to negative x. That would be the equation of that line in the xy plane, but then once you add in the third coordinate, z, that becomes the plane. Now let's take a look at triple integrals in cylindrical coordinates, or maybe I should say more triple integrals in cylindrical coordinates, because we did see a couple in lesson 26. Here we're asked to find the center of mass of the frustum of the cone, z squared equals x squared plus y squared, between z equals 1 and z equals 4. And notice here, they're not giving us the density function, so we could assume that the density is constant and equal to 1. So we're talking about the part of the cone we have here between z equals 1 and z equals 4. And we're looking for the center of mass. Now, by the symmetry in x and y around the z-axis, we can guess that the x and y coordinates of the center of mass are going to be 0. But what's that z coordinate going to be? That's what we really want to find out. And by looking at the shape of our solid, we should have an idea of approximately where that z coordinate would be. For example, it's not going to be halfway through the interval from 1 to 4 because there's much more mass on the top of the solid near z equals 4 than there is down by z equals 1. So we know that the center of mass won't be halfway through the z interval. Maybe it'll be 2/3 of the way through. If we're going from z equals 1 to z equals 4, maybe the z coordinate will be approximately 3. But we'll find out for sure by using the triple integral. So our guess is that x bar is equal to 0, y bar is equal to 0, and we're pretty confident about that, so I'm using an equal sign here, and that z bar is approximately 3. And now let's see what we get by making the computation. So we're calling this solid, this region in three-dimensional space, so we're calling that D. So z bar is equal to 1 over the mass of D multiplied by the triple integral over D of z times the density function, which we're saying here is just 1. And the mass of D is equal to the triple integral of just the density function, or just the function 1. So let's start with the mass computation. And just like we did with the problems in lesson 26, we want to start with our variable z as the inside variable. So let's take a look at what the bounds would be on z. Here we have the plane z equals 4, and that's our top surface. But what's our bottom surface going to be? We actually have two different bottom surfaces. We have z is equal to radical x squared plus y squared as a bottom surface, but that's only going to be the bottom surface for points with r between 1 and 4. For points with r less or equal to 1, the bottom surface is going to be z equals 1. So we realize that we have to break this up into two integrals. And because we want to break this up with bounds on r, we can see that it's going to be easiest for us to describe this domain in cylindrical coordinates. So this z equals radical x squared plus y squared becomes z equals radical r squared, or just r. So for r between 1 and 4, z goes from r, the bottom surface, to z equals 4. And for r values between 0 and 1, z goes from 1, the bottom surface, to z equals 4, the top surface. So let's take a look at what our integral is going to look like for mass in cylindrical coordinates. And keep in mind that this dv we know is going to be dz for our first variable, and then r dr d theta. So we bring the r out front, and this dv gets replaced by r dz dr d theta. So for r between 0 and 1, we have z going from 1 to 4. So z goes from 1 to 4, where r is going from 0 to 1. And then theta, in both cases, is going to be 0 to 2 pi. Now for r between 1 and 4, we have z going from r to 4. Z goes from r to 4, r goes from 1 to 4, and again, theta goes from 0 to 2 pi. And so together, this computation will be the mass of our domain. So let's compute. Integrating on z, we're here. And then on r, and then on theta, we get 21 pi as the mass of the solid. And so our computation for the z-coordinate of the center of mass has a 1 over 21 pi on the outside. Our bounds are the same as the bounds on the other integrals, but now we have z with the r inside the integral because we're again looking for the z-coordinate of the center of mass. Again, we integrate on z first. Then on r, and then on theta. And we get 85 over 28, which is approximately 3.0357. So our guess of 3 was a pretty good guess. And this is z bar. And we said we expect x bar and y bar to both be 0, and you can compute those as an exercise. Now let's take a look at evaluating an integral by changing to cylindrical coordinates. So if we already have this integral set up in rectangular coordinates, how can we change to cylindrical coordinates? Well, there are a number of things that we have to do. First thing we have to do is change the inside function from x and y to r and theta. So we're going to want to change this by replacing x squared plus y squared is equal to r squared. Then we want to change the bounds on z also so that they're in r and theta coordinates. So that means this top function here is going to need a 2 minus r squared. Then we want to use the bounds on x and y to draw the region in the xy plane. So we want to take these other two bounds and see what region that describes in the xy plane. Then we want to redescribe that region in polar coordinates. And then we want to make sure that we remember to put in the r with r dr d theta. So let's take a look at how we can change this integral to cylindrical coordinates. We said the first thing we want to do is to change this to r squared. We're going to have radical r squared, which is going to simplify to r, because in our case we're only considering r to be greater than or equal to 0. We know that our dz, dy, dx is going to be r dz, dr, d theta, so we have an r squared then. We want to change our bounds on z to be written in terms of r and theta. So we have 0 and then 2 minus r squared. And then we want to take a look at this region so we can describe it in polar coordinates. So let's see what we have here. We have y going from negative radical 1 minus x squared to positive radical 1 minus x squared. And with that, x goes from 0 to 1. So what region is that in two-dimensional space? These are the equations for the top and bottom semicircles. So we've got the unit disk here. We've got y going from negative radical 1 minus x squared to positive radical 1 minus x squared. And then with that, x goes from 0 to 1. So that means we only want to shade in the right-hand side. So this is the region that we're talking about here. So now we need to describe this in polar coordinates. So because it's a unit disk, we know that r is going from 0 to 1. And then theta, we want only quadrants 1 and 4. So the easiest way to describe this would be to say theta from negative pi over 2 to pi over 2. So now let's put these bounds in our integral. R goes from 0 to 1, theta from negative pi over 2 to pi over 2, and now we can compute. So we integrate on z, plug in our bounds, subtract, and then on r, and then on theta, and we get 7 pi over 15. And this concludes our lesson on cylindrical coordinates.